I'm Franco Brezzi, and I'm the chairman of this session. And it's a real pleasure and honor for me to introduce my colleague and friend, Ferdinando Auricchio, that I consider as one of the few jewel researchers that can be fully considered as both as an engineer and a mathematician. And so there aren't that many of them, and I'm very glad to be a friend of him. Well, he also, being a friend, asked me to be as short as possible. But okay, I cannot avoid to give you some few essential pieces of information. He was born in Naples in 1965, got the bachelor at the University of Naples in 1989. Then he moved to University of California, Berkeley, where he got the master in 1991 and the PhD in 1995. And the academic career that he got started in 1994 as an assistant professor in Rome, Roma Tor Vergata, which we call Roma 2. And but then already in 1998, in Pavia we had the stroke of luck to be able to acquire him, and so he has been there ever since. First as an associate professor, and then starting 2001 as a full professor. In Pavia, he was also an associate researcher of IMATI, Institute of Applied Mathematics and Information Technology, which, this in his own panorama of his accomplishments is a minor dot, but I'm proud of it because I was the director of the institute, and so I'm very glad to have succeeded in convincing him to be with us and help us in research. And if you look at his CV on the web, you find exactly what you expect. That he has been a member of a lot of important cultural associations, panels, committees. Possibly, I would say that if I have to mention one, vice president of ECOMAS since 2013. He is a member of the editorial board of about a dozen of the most prestigious journals in engineering and scientific computing. And he has a lot of recognitions, prizes, awards, and various types of recognition. But since he is so good, I think that now, for me, the best thing to do is to shut up and give him the floor. Okay, so, ladies and gentlemen, Ferdinando Auricchio.
Thank you very much, Franco. I hope you were going to be much shorter, but and they say that the most important accomplishment is to be friend of Franco and to interact with him on different subjects. So, ladies and gentlemen, good morning. First of all, I would like to thank the GAMM Association for, and in particular the president, Professor Wolfgang Heller, for this invitation. And I would also express my appreciation to the local committee of the conference, very nice conference, and in particular to Giorgio Zavarese, who has been doing a great job in the conference. So my presentation, when I was invited to give this lecture, it's always difficult to choose between different subjects. So quite often I end up with Shimmer alloys, and so I decided to arrange the presentation as a two-part presentation. And in the first part, I will talk about. Do you see the red dot, or you want me to use this? You see the red dot? Okay. So I will start to talk about Shimmer alloys, and This is an old story for me because I start to work on this subject in the old dates for me, which means already in 1993 I start to work on shell alloys during my PhD studies at Berkeley. And however, shell alloys has been for me a very seminal activity because it has brought to my attention several other subjects. So the idea here is to talk about shell alloy and to show you how, starting from shell alloy, we got interested in many other areas of activities, so solid simulation, fluid simulations, comparison between numerical and experimental, and more recently, rapid prototyping. But let's start from shell alloy, and I think that most of you know what shell alloy are, but I want to be inclusive, so I will go through classical definition and an overview of the material. So shell alloys are metals with an intrinsic ability to recall an initial shape also after severe deformation. That's the main definition, and from the macroscopic point of view, these materials are able to show two unusual effects which are not available in traditional materials. And the effects are named the superelastic effect, which is the ability of the material to undergo a large change of shape when it's loaded, and then to recover the original shape when it's unloaded. So in a stress-strain diagram, you usually have this type of pattern. The other effect, which is also quite unusual, is the Shimmer effect. Following the Shimmer effect, you can take a piece of material, you can mechanically load and unload. At the end of the loading and unloading, the material does not recover the initial shape through the unloading, but it can recover the initial shape through thermal heating. So in a stress-strain temperature diagram, you have the loading and unloading, you have some permanent deformation which is fully recovered or almost fully recovered with heating the material. So clearly these are two effects which are not available in traditional materials, and I lost the dot here. In traditional materials, and these open the door to very innovative and commercially valuable applications. In particular, because you always have to recall that these are metal alloys, so these are materials with high mechanical properties and high work output. So since they're metal, they can really perform work. And there are many applications which exploit these material features. So, for example, in the superelastic range, which is the one described here, a very classical application is the one in the eyeglasses frame. You can really crush the eyeglass frame, and once you release them, they recover the original shape. Okay, this is a very clear and nice application. However, this effect is exploited in many devices adopted in non-invasive surgery. For example, thanks to superelasticity, you can bend the material also with a small radius without obtaining kinking. And that's a very intriguing property that is used when you have, for example, in the human body tortus anatomy, like this one, like this channel, and you want to insert an instrument on this side. You want to go through all the channel, get that down here, do some job, and you want to keep controllability of your instrument. So you want to insert the thing, and then from the outside the human body, you want to still work inside the human body. And in fact, there have been many cannula, catheters, guide wires made of Shimmer alloys, biopsy forceps, and so on. On this concept, another application which is very interesting for me is the possibility of obtaining flexibility without hinges. This is really exploited, for example, in biomedical fields, again, when you have many gripping systems like this. So you have a system which can grip elements like stones without any hinges. And this idea, the same concept, has been exploited also in so-called compliance systems. So you basically have elements which reproduce this concept of an hinge without having really an hinge. So you can really have flexible elements, and you can reproduce an hinge effect without having really something that should some pieces that should rotate one on the top of the other. However, for sure, the most well-known application is within vascular pathologies, and for example, when you have a stenosis, so you have an occlusion of a lumen, nowadays very adopted concept is to go inside the vascular system through a peripheral access. So it's considered a non-invasive type of surgery. So you go, for example, through the femoral artery. You go to the location where you have the occlusion, and you can release a stent. A stent basically is a tube-like scaffold which is able to open up the lumen and to make the blood go through again through the vessel. And the same concept is also exploited in many different devices, adopted in vascular pathologies. And here you can see very high complex geometry obtained through these materials. However, it's not only biomedical that has nice applications. You have nice application also for structural systems. The use of this material has been exploited also to isolate structure from vibrating support, taking advantage of the dissipative and self-centering ability of the material, as well as bridge restrainer or as a system to induce a compression state, a controlled compression state for masonry. So many applications taking advantage of the superelastic effect. However, there are also many applications taking advantage of the Shimmer Effect. So the ability of the material to recover the shape, however, only when you heat it up the material. A very classical example, very explicative, is again eyeglasses frame. Once it's deformed, you just only put under hot water and you recover the shape. There was a very interesting project to use such a material to elements to break big stones instead of explosives. So here you can really appreciate the power of this material, the ability to produce work of these materials. But the more interesting application are when you induce this recovery in a constrained form. So basically consider if you start from a spring like this, which is, in the original configuration, let's say it's a long spring, you can compress and make it short. Then if you heat it up, the spring, it will go to the original shape unless you put a rigid constraint. So if you put a rigid constraint, the spring will try to elongate, then it will be in contact with the constraint, and what happens at the constraint is that, it will start, there will be a rise of a force inside, acting inside the spring and acting on the constraint. And this constraint recovery concept has been used in many different applications, for example, for joining different materials, but also in critical situations where there is not enough space to really join many elements. However, again, the constraint recovery concept becomes even more interesting if you don't couple your material with a constraint, but you couple with a contrast element, so with an element which is able to do a work. And for example, we can look at this picture here. So if you start from a spring, now I consider a spring which is short, you apply a load at this spring and it gets elongated, so it gets a much longer spring. And if you keep the weight constant, if you heat it up, the material, for example, through some joule effect, you heat it up the springs try to go back, but due to the presence of the weight, is not able really to completely go back, so at least it's shortened a little bit, but when you heat it up, it goes from this configuration to this configuration, but when you cool it down, due to the action of the weight, it goes back here. So basically you have what's usually named a two-way Shimmer effect, because it's repeatable. So thanks to the presence of the force, you can heat it up and cool it down several times, so you can go back and forward, so you're producing an actuator. And you can very easily have a linear actuators, angular actuator, and other things like that. And what is really interesting is that if you look at for the car industry application, there are, in the modern cars, there are so many actuators already used that you can really imagine the impact that this technology can have and is having now in many industries. So all these applications, clearly show you that in many situations you have a complex material behavior. Sometimes you have a complex geometry. Even the spring, it's quite a complex geometry because we are very used to springs, but once you couple this geometry to the nonlinear behavior, to really understand what's going on these elements is not easy. So it's really important to have three-dimensional computational tools which should be effective in reproducing the material behavior and should be also very effective from the modeling point of view, in the sense that they should also be able to reproduce the material behavior in a general three-dimensional context. So for us, it's very important not only to reproduce the material behavior, but also to make it available, these tools, in a real computational framework. So to do the development of constitutive models, the first thing the path that we always follow is to try to understand a little bit the micromechanics, not too much, otherwise the modeling gets too complex, at least for me. So we always approach the modeling from a microscopic phenomenological point of view, and then we try to develop models which are computationally effective. So in terms of micromechanics, just few very minor concepts. To understand the very unusual material behavior, you need to consider very few key things. And the basic ingredient you have to understand is that the material has such unusual effects because inside the material there is a reversible crystallographic transformation. So the material is able to produce, to show this reversible crystallographic transformation. That is a solid-solid phase transformation, which is also named sometimes Martensite phase transformation. So basically you have two phases, a martensite and austenite, and the material is able to transform, with certain feature, from martensite to austenite and back. So the martensite is a phase which is stable at lower temperature, and in general is characterized by a low crystallographic symmetry. The austenite instead is a component which is stable at a higher temperature and is characterized by higher crystallographic symmetry. So here I indicated like a square for the higher symmetric austenite, and this skew element for the lower crystallographic symmetry for the martensite. And basically, understanding that the material can go back and forth between these two phases, solid phases, you can really understand what's going inside the material. Also, if you really want to understand the micromechanics, clearly the complexity is very profound. And just to give you a glance, consider that the material in reality doesn't go from austenite and martensite and that's it. But there are many intermediate configurations which are possible. So there are intermediate phase transformations which may occur. Moreover, once you have the less symmetric configuration, this less symmetric configuration clearly can self-organize in order to accommodate the surrounding conditions, so you can end up with very complex pattern at the microscale. So the question is how much details of the macromechanics we want to bring into the modeling. My point of view is always try to bring the less we can, as long as we are able to reproduce the macroscopic effect. So in terms of modeling, here I want to review very quickly a model we've been using a lot in the last years. It's becoming a quite old model, but I really like it. It was originally proposed by Sousa in 1998, so it's really getting old. It's a three-dimensional phenomenological model. It's based on introducing some control variables. As control variables, the model uses the strain, the second-order strain tensor, the temperature T, and use only one internal variable. This is a second-order tensor, and it's named transformation strain, ETR, okay? So it's just one variable. It's quite, in some sense, a rich variable because it's a second-order tensor, but it cannot really capture all the micromechanical complexity. And in fact, if you choose only this internal variable in your model, only this quantity as internal variable in your model, I mean, you cannot get a huge description of what's going inside the material, and you can only try to describe what I name a generic parent phase from a generic product phase. So you don't get a very good description, but we believe it's already enough for many applications. So the generic parent phase is basically a phase which are all the phases which are not associated to macroscopic strain, while the generic product phase are all the phases which are associated to macroscopic strain. So we don't do any deep distinction what's going on inside the material, but just we distinguish between these two quantities. If you consider this internal variable, I mean, this internal variable is naturally should naturally satisfy a constraint, because since we are dealing with a material which undergoes a phase transformation, this variable cannot evolve indefinitely. Cannot evolve forever. So it should satisfy some constraint. And the constraint is here indicated. So basically, the norm of this internal variable should be bounded above from a material property, from epsilon L, which is a material property. So, which means that the material can either be in the situation where this variable is 0, so the norm of this variable is 0, or it can transform. But once the full material is transformed and oriented, you cannot proceed with more transformation. So it should be bounded. So once you pick up with this, once you agree to work with this very simple set of variables, the model it's proposed, and Helmholtz started to work with the Helmholtz free energy, which is composed by a bunch of terms. In red, I reproduce the terms which are very classical, so I will not point your attention on the red terms, but I will point your attention to the blue terms, which are in some sense, at least for some community, they are more interesting. So the first blue term is this one. This is the chemical energy. Is a quantity which should reproduce, effect from the Martin-Cyclic transformation. And in particular, this term is interesting because it's linear in the norm of the internal variable, which is kind of unusual in some standard plasticity model. And it's beside, the linearity in the norm of the internal variable, there is this other factor, tau m, which is chosen in this form down here. So this, you don't see probably very well the Macaulay bracket. This is basically the positive part function. So the tau m is a function of temperature, is piecewise linear function of temperature, and when T is below T star, this term is 0. When T is greater than T star, these terms varies linearly with T, and the dependency with temperature above T star, depends on this material parameter beta. So here there are two very important ingredients, material parameters, which are T star and beta. The other term which is interesting is this quantity here, which is the indicator function, which can be seen as a mathematical tool to take care, in a sense, automatically of the constraint on the transformation strain norm. Okay? So that's the free energy that's adopted. Then using standard argument, you can derive the stress, the deviatoric part of the stress. More interesting, you can derive the thermodynamic force associated with the internal variable. Here is the expression. Let me point out just that it's function clearly of the internal variable, and in particular at the denominator here, you see the norm of the internal variable. And that's a source of problems because this quantity can be 0. So clearly we need to regularize this expression. Once we derive the deviatoric part of the stress and the thermodynamic force X, borrowing concept from classical plasticity, we can introduce a limit function, we can introduce an associative flow rule, and the standard Kent-Taggart condition, and clearly we can choose also quite nice limit function, very classical from the plasticity world. Okay, so that's a very simple model. Once we develop all the equation, we can start to play with the model. In particular, as I say, the first thing you have to do is to regularize the norm, because you have the norm the denominator, so you don't want to have something divided by 0. Then, since we're really interested into the numerics of these models, we develop an integration schemes. So you take all the system, in particular the rate equation, you integrate, as classically done with implicit backward Euler scheme, and you obtain a system like this, which is, in some sense, is very similar to plasticity. But the point is that beside the standard Kent-Tucker condition, which we are very used, which we know how to treat, there are other constraints, other inequalities, which comes from the constraint on the norm of the internal variable. So the problem we need to face is, in some sense, is more complex than standard plasticity because it's more nonlinear. So the point is to really understand what is the algorithm to develop, and if we are able to develop an algorithm which is able to manage all this nonlinearity. And however, for such a model, we were able to devise what I name a two-stage return mapping algorithm in order to, we have, let's say, 2 trial states in order to see if, which constraint is really active. So for this scheme, for this model, we can stay within the return mapping algorithm, and you can extend the classical plasticity return map algorithm in order to devise a sufficiently robust numerical scheme. But in any case, let me stress that this model is already it's not too easy to treat it numerically, and you can come up with some problem. And so when we were working with this model, I already had a question in my mind how to generalize it for example, for multiple phase transformation, because the model I'm presenting here, I believe, is a very effective model, very interesting, but you always want to do something more complex, not too complex, but a little bit more complex. And my feeling was that to have a return map algorithm for this model was already at the limit of the return map algorithm. So, but let's focus on the model. So once we develop the theoretical frame, we develop the numerical scheme. Clearly, you can try to match your material parameters against experimental data. So let me point out again the material parameter of the model, in which I was kind of fast. You have some elastic quantities, the standard one, elastic modulus and Poisson ratio. You have beta and T star, which already introduced. And then you have 3 other quantities. So you have a total of seven material parameters you have to choose to make this model run. And, this is a very limited number of parameters. So beta and tau star, tau star, as I told you, it was appearing in the definition of the tau-m function, is the temperature below which basically you have the Shimmer effect. Above tau star, you start to see the superelastic effect. Beta is the dependency of this slope with temperature, so it tells you how the material changes with temperature, and then, for example, H gives you a measure of the slope of this phase transformation region, and R give you a measure of the width of this region, so of the width of the hysteresis region, and M is a quantity which describes the difference between tension and compression. So very few parameters that in any case needs to be calibrated. And when you want to calibrate it, we start to calibrate it. Here the picture doesn't look too great, but basically we always use a strain temperature diagram, which are the basic diagram used by companies to test actuators. So when you really study actuators, the actuators I was showing you, the spring with the weight, the way they really use to experiment on this actuator is to see how the material behave in a strain temperature diagram. And here you can see the smooth curves. These are experimental data. And you can see, the fitted curve from our model, and we can calibrate the model, and we can use this material parameter to do much more, very, very complex simulation, as I will show you. However, as I was mentioning, the model I discussed originally due to SUSE is a very simple model. You can see from this diagram. Basically, this is the classical diagram in a stress temperature diagram, and in green you see the phase transformation region. So a very simple model, very few parameters. Unfortunately, it's a very nice model. It's not completely effective in all the applications, especially when you want to simulate actuators, because clearly companies, what they do, they design their actuators to work exactly in this region. So they put a load, they fix the loads, and then they vary temperature. So they really put themselves at this level, and that's exactly the region where the SUSE model is not tremendously effective. So we decide to try to come up with a more general model. In this more general model, we somehow uncouple the different phase transformation. So we try to model the single variant transforming to austenite, the austenite transforming to single variant, the multiple variant transforming to single variant. So we try to be more effective in trying to capturing the micromechanics. And however, if you try to do this, clearly the model gets much more complex. So when we start to develop this new model, my question was always, are we able to really do the implementation, and how can I do the implementation? But as the first thing, let me show you the model. So that's the phase, that's the stress temperature diagram where you see all the phase transformation occurring. So you appreciate this much more complex model with, for example, phase transformation which can interact, overlap, and the idea was to get something where you can really compare with experiments without having any worries. You want a model which is thermodynamically consistent and numerically robust, without being worried if, for example, this region is really on the left or on the right, or about the slope of this region. So you really want something that's robust theoretically and robust from the numerical point of view. So we start to work with some colleague from mathematics in Pavia, and we develop a model which is, in some sense, it's not a much more complex model. It doesn't look like a much more complex model because you use just one second order tensor as internal variable plus two scalar. So the internal variable is the direction of the martensite, and then you have two scalar variables, which for example could be the fraction of the multiple variant martensite and the fraction of the single variant martensite. So compared to the previous model, basically it's like we are just adding one extra scalar internal variable, so not much. Where is the complexity coming in is in the free energy, because we really try to model the free energy without any constraint on where the phase transformation are placed. And I don't want to go clearly inside the details, but here, for example, let me point you just a few things. Here, for example, you can see two indicator functions because you have more internal variable, so more constraint to satisfy. So you have, clearly the complexity, the equation gets more complex. But again, what was really worrying me at the beginning is that you have more internal variables, so you have more thermodynamic forces, you have more yield functions, you have more nonlinearity to deal with, so to understand when the different phase transformations are active or not. And so the question, the point was that it was clear to me that it was impossible to really to come up with a return map algorithm, a standard return map algorithm to solve, to consider all the different possible situations in which you could be with all these nonlinearities. So the idea come because there was some colleagues pointed out us the possibility of transforming the inequality problem into an equality problem. Okay? So using the so-called Fisher-Bernstein complementary condition, if you have a problem like this, where you have these inequalities which should be satisfied, you can transform this inequality to an equality problem. And so the idea we had was to really take all the inequalities, all the inequalities we had, each one, transform in some equality, and then multiply all of them, and then let's say we were ready to pray and see how the algorithm was going to work. But since my feeling is that since the model was really thermodynamically consistent and well designed in a continuum and mathematical framework, all these manipulations lead to a very robust numerical scheme. So the thing we did, we integrate the rate equations again with the backward Euler scheme. We end up with a huge number of equations now, and we decide to solve this highly nonlinear system with a Newton-Raphson scheme, and to make the system automatically on its own to decide what is really the active phase transformation, if there is only one active phase transformation, or maybe two active phase transformation, and so on. And we also had to use some smoothed Fisher-Bernstein function because we have some singularity. But in any case, what was extremely interesting is that the algorithm seems to work fine for all the simulation we are performing. And as I'm going to show you, we are running some nice simulations. And in fact, the model was performing so well that we also start to introduce more complexity, like a dependency of the elastic modulus on the Martenside fraction, a smooth transition of the yield condition from the elastic to the phase transformation region, variable hysteresis width. So we really increase the complexity of the model to match the material performance, and we still use the same numerical scheme. But let's start to see some numerical examples. Here you can see again the experimental data produced as the one I was showing you before. I forgot to mention that they were produced by Professor Sittner within a European project. And here you can see in black dotted the smooth curves, which are the experiments. You can see the original SUSA model in blue, and you can see the new model, the proposed new model, and you can see, these are very simple tests because these are uniaxial tests, so they're very simple, but clearly you can see that we get a much better fitting between the new model and experimental data. SUSA is also doing, a nice job, I think, but this new model is doing much better. We compare not only with the data produced by Professor Sittner, but we have a long-lasting collaboration with SizeGetter. SizeGetter is a company in Italy, very close to Milano, and they are the world leader producer of shame alloys nowadays. So we have a collaboration with them. Here you can see other uniaxial tension tests produced by SizeGetters and our comparison with their experiments. And we also calibrated the model for reproducing the behavior of spring actuation test. And here you can see a bunch of dots with different colors. Each dot is basically a different spring or a different spring under different conditions. We calibrate the model using just one curve, and we're fully able to reproduce the behavior of the spring under different conditions. So the company was quite interested on our simulation ability. But once we have this numerical tool, clearly we got interested in more complex structures. And as I told you, shame alloy for us was for very seminal activities. And the first application I've been looking since a long time ago is stents. So it's these grid-like devices which vascular surgery put inside the human body in many situations. And if you look at the literature, a very common way that stent producer have to test the device is to take the device and bend it. So they simply grip it on the two sides, and then they they pull down one side, and they bend the stent, and they, as you can see here, they have some instability effect. So the goal was to try to build up a numerical scheme for this geometry, which is quite complex, and try to see if we can reproduce this effect. And so we start, we start from a micro CT scan of the real geometry. We develop a finite element mesh and IGA mesh, and we run the simulations. And as you can see, we can qualitatively, from our numerical scheme, we can very well reproduce the experimental results. But again, this was, in some sense, was a seminal work, because it was very interesting to, the more we work on this area, the more problem we face and the more interesting things we found. And here is something I would like to share with you, which was kind of astonishing. We did this simulation, so we did this bending simulation with standard finite elements and with IGA, the isogeometric analysis techniques, using FIP in both situations, and we really tried to crunch down numbers. And what was really incredible is that, for this structure, it's extremely difficult to get to a convergent solution. So we start with finite element analysis, and we refine the mesh, and, it was very difficult to get to a convergent solution. Even more interesting, you can see that the convergence is not smooth. It doesn't go really in a nice way, and that's because for let's say crude mesh, which are already with quite a large number of elements, but for crude meshes, you don't get the pattern of the stability. So you really need to go above, for finite element, above 10 million degrees of freedom to really capture this pattern. And even for such a high number of degrees of freedom, we are getting close to convergence, but we are not, almost there. And instead, IGA, is really doing a great job. So it's interesting that even for this structure, which seems very simple from the applied point of view, vascular surgery are, putting this device, I don't know how many of them every minutes in Lecce, they use probably in the hospital, they put one of those every 5 minutes in a patient. So to do really the simulation of this device is extremely complex. They're very tiny, small devices with very small elements, so it's really complex to do these simulations, and even the numerical tools that you want to use maybe are not, you need to play with these tools with some caution, and you need to have a very refined numerical schemes. But I was telling you at the beginning, Shimmer alloy has brought to our attention many different areas, and in particular in the last years, again, from our interest in Shimmer alloys, we've been interacting more and more with doctors, and we are trying to use our numerical tools to really interact with doctors and try to make for them the possible to use our numerical results. So the concept we always try to use is that we believe that we can do a lot of simulations, but we always want to start from very realistic situations, so really realistic pathological situations. So from patient-specific medical images, we want to start from very accurate geometry for the prosthesis that we simulate. We want to do our engineering job, which is the simulation, but then we really push very hard in order to elaborate the results and to end up with some clinical evaluation to give to the doctors. However, even these engineering aspects, this engineering box is really complex to perform. And it's really complex because I'm showing you here two applications, which we are exercising more and more ourselves. Here is an aortic endografting. So you can see here an aorta. That's a real patient. The real images. That's CTA from a patient, and you can see that there is quite pathological situation. Here is better details. You can see the false lumen. Basically, I mean the situation here is really pathological. So what vascular surgery do? Using a peripheral access, they release inside the patient aorta. They use an endograft. An endograft is basically a stent, as before, with some tissue around the stent in order to eliminate from the flow the aneurysm. Okay. So the idea is to really simulate the deployment of this Shimmer alloy device inside a real patient. The very nice thing is that we can get from the doctor the preoperative situations, and for the first patient we can also get the real postoperative situation. So here again it's a real is in images from the real patient after surgery, and you can see here in light blue the device which has been placed. Okay, so the idea is to start from these images, preoperative and postoperative, to construct our models for the vessels, our model for the device we want to implant. In this case was even very interesting because it was a patient-specific device. So the company produced a device for the specific patient, and in fact it's a very strange geometry. And then we can do the simulation, and we can the same simulation from two different perspectives. So we can really do the simulation and simulate the implant of the device. And here you can see a qualitative comparison between the simulation in the upper row and the reality, and we can try to get a feeling how good is our simulation and how close we are in predicting what's really going on inside the patient. And here is a very nice, what I believe is a very nice picture, because we can really put the two images one on the top of the other, and using some cross sections, for example, for this cross section, we can compare what's going on in the simulation in terms of radius, what's going on in terms of reality, the dispersion of the radius, and so we can really, for different cross section, we can compare simulation and reality and try to get a feeling how close we are to what was really going on inside the patient. This simulation, in any case, is done with rigid walls, so the device is flexible and implanted, but the walls are rigid. Clearly, the doctor were also very interested not only in the stent apposition, but they were also very interested in the fluid dynamics after the implanting of the device. Here is another patient. Preoperative situation, postoperative situation. They put more than one endograft here, so they have. The patient has a very long stented part of his body nowadays. And the question that was raised by the doctors in this situation was the so-called bird beak. So since they placed the device also in the aortic arch, the device was protruding a little bit inside the arch, so there was getting some sort of turbulence here, some turbulent effect, and the doctors were kind of worried, and they asked us to quantify these recirculation effects. So again, we did some simulations for them, and you can try to come up with some few numbers to really show the doctors and communicate to the doctors. And these simulations are really very interesting, very intriguing, but they're incredibly time consuming. At this moment, we are doing many of these simulations, but this type of simulation we again go up to above 10 million degrees of freedom, and each of these simulations for 6 cardiac cycles, it takes about 3 weeks to run it. So computational, they're very heavy simulations. The other thing which is really demanding is that the doctor doesn't want to have one simulation,
but we are working with very large hospital in the Lombardy area. They have a bunch of patients, and now we have a tool that they use. So every time they see a patient where they have a question, which is basically for each patient, they click on the images, they send us through the web the images, and we can do the simulation for them. Unfortunately, a very long time. But the very nice thing is that we are building a database of patients. So we are building really a quite large database of patients. We are building images, preoperative images. We are building this. We are getting both CTAs and MRI. Post-operative, and we are running all the simulations, and we are learning. It's a very learning process. So it's a learning process for the behavior of the devices, again, made of shell alloys, but it's also a learning process because each of these simulations is very time-consuming and each one is different from the other. And as you can see here, you can have, for example, very complex situation. This is a patient with 3 different aneurysms. And here they have a big question because should they operate or not? Should they do some surgery on this patient or not? So we are running the simulation. We are discussing with the surgery and probably in a short time also with the patient. What's the real situation? Clearly, once you start to see all these pictures, all these colors, especially due to the complexity of the situation, the question I keep asking myself is, are all these simulations reliable or not? Or how reliable are they? In terms of devices, we can do easily experiments. So we can take a device, we can take a piece of the device and do a traction test to see if our model are matching the response of the device. We are running also a quite large campaign on human tissues and animal tissues to learn about the material properties of the pathological human tissues. But clearly, again, there is always a question, how reliable are the simulations? And that's one of the reasons because we're getting more and more into medical imaging. And here is the patient I was showing you with multiple aneurysms. You can see, here, you can see the MRI, the data from the MRI, the dynamic MRI, and here you can see our simulations, and we are really trying to compare. We are trying to use MRI not only as a good tool to include boundary condition in the simulations, but also as we are starting to use MRI as a tool to compare our simulation to the reality and learning, go with the learning process. Clearly, this technique of learning about the device, learning about the patient, learning about the pathology can be done for many different districts. So in the group we are working also on carotid stenting, coronary stenting, aortic valve surgery. It's here represented. It's a very active area for ourselves. We have a popliteal aneurysm. So there are many different vascular districts which are interesting. But again, all these activities always bring more activities. So every activity we do, there is more thing to do. So the last area in which we're really getting involved and which I'm really falling in love is rapid prototyping, which is normally named as 3D printing. So basically, what you do in 3D printing. You start from an image. For example, you can draw an image on your computer. You do a virtual slicing, and then you take these machines which produce for you the component. Okay, so from the virtual world, you can physically produce a component, and here you can see, I took from the web. Now these machines are becoming more and more common. Basically, it's a fused deposition machine. So it puts some materials. You can reproduce very complex geometry. This is one of the 3 machines we have in our lab. And from medical images, basically, we are learning how to print these components. Okay. So here, for example. You can see exactly the aortic arch I was showing you before, or maybe not. I don't remember if it's exactly the same, but again, here you can see the images, the images of a real patient aortic arch, and here you can see the element we printed. And the reason is that, again, we want to validate our simulation. So we want to use these components and try to experiment with these components with our vascular surgery. In these days, we have some vascular surgery coming to our engineering lab, and they're really working a few days a week in our lab, and they are experimenting, for example, to deliver the device on a specific patient. So they're learning how to deliver the device, but they're also trying to optimize the surgery before really performing the surgery. And again, from one idea, there is another idea coming. And here is another activity on which we have been working. Since we are able to print this, to 3D print these vascular components, we built up also a new lab, which is a lab for biomechanics for the vascular treatment of the aorta. Basically, we have a pulp plus valves. We have some systemic impedance, but in a few words, what we're able to do in one of this district, we are able to experimentally reproduce the physiological or the pathological situation of our vascular districts. And here, and that's my last thing I want to show you, here is an excited pig aorta placed inside our hydraulic systems, and you can see that it's a pulsatile system. So basically, the idea is to use the 3D printed components to plug inside these pulsatile systems. And something I'm not going to show you today, but we already did it, we can bring the whole system under MRI, so we can really do, so we can do MRI of the patient before operation. We can ideally print the district of the patient with the 3D printer. We can put the 3D printed, for example, aorta inside the system. We can bring the system under MRI and see what happens. We can do the surgery on the 3D printed aorta and so on. So again, everything started from Shimmer and alloy, but it's growing. And clearly, all these, I'm here talking, but all I'm talking about can only be done through the collaboration of many people. So I would like to show you this picture, which was taken a few months ago in Pavia. These are the postdoc and the PhD students working on the thing I was showing you, and I really like this picture because everyone is smiling, and I really love it. And here is a bunch of names, so the people appearing here. These are the engineering group, but there is many collaboration with companies, and in particular with the hospitals in the Lombardy region, but also in Europe. We are interacting with several hospitals now, also in the United States. You can find all the information on our webpage. And this really comes to the conclusion of my presentation. Thank you very much.
Yeah. Thank you, Ferdinando, for the very interesting, exciting stimulation lecture, also perfectly on time. And so we might have...
I hope clear also, I don't know.
Yes. And so if there are any questions, we have room for maybe a couple of them.
You can very easily get to a much more complex model, but it's, if you really simplify, you end up with plasticity, but it's adding up pieces and pieces. But it's a general plasticity model, no question. That's the reason because I like the original model also, because it was very plasticity-like.
Ferdinando, could you shortly comment about the features and advantages of your model with respect to other ones existing in the literature, at least as far as the first model is concerned in terms of internal variables, like Woodard's model or bands and so on. Can you shortly say something?
That's a difficult question because it's a difficult question. Fortunately, SUSA model is not my model, so I can say I really like it because otherwise, everyone likes his own model. But it's the original model, the SUSA model, and I really like it because it's very, very simple. So I know, especially recently, beside the work by Lagudas, which always proposed very interesting models, the main issue is to come up with a model which is effective from the prediction point of view and from the numerical point of view. So the original model, I really like it because it was very, very, very simple. Recently, there has been very nice contribution from Professor Sittner, the group of Professor Sittner, and from Stanislaw Sulikiewicz, because what they did is what I really like about those models is like, the question from Professor Del Piero is that, I think that you can easily come up with nice models that can reproduce everything, but to make robust from the numerical point of view, they should be absolutely consistent from the thermodynamical point of view, so they should be put in a very nice frame. Otherwise, numeric will never work. So the nice thing about, I think, what we're doing and the contribution I was mentioned by Sittner and Sulikiewicz is that they are very nicely in the direction of models which are in a consistent framework, which is based on dissipation potential. So the original model was very simple, it's 7 constants. The model by Lagudas, they are wonderful, they're not too easy to implement, I would say. They have a different description between forward and reverse phase transformation, so it's not very easy to code them. So if I would say I prefer the one by Sittner and Sulikiewicz or the one we're working these days. But I mean he's an expert on the subject. So.
Can I ask a second question? As you know better than I, the first model for these changes was a model of Ericsson based on nonlinear elasticity. Of course, the dissipation mechanism was missing.
Yeah.
And my question is, which is the relation of your models to this primitive model?
That's a difficult question, which I don't know the answer, I should say. So it's not. I don't know the answer. Sorry. So
it is a double question.
It's at least for me, it's not a question. So you mean for the? As you say, there is no dissipation there. So if there is no dissipation, you cannot do any numerics because you cannot simulate the evolution. It's unstable. I don't think I should look at that. The key ingredients of these models are the 2 points I will show you at the beginning. So the fact that you have a term of the free energy which is linear in the norm and the indicator function. These are the 2 ingredients, and I don't think that the Ericsson model has the indicator function. I don't know about the linear term. Maybe not either. Because I don't think so, because it was just this model. I know the family of models. I don't know the specific. I don't remember. I read it a long time ago, so I don't remember exactly those models. But
there are people like James, for instance, in the wonderful results based on that model. So I am wondering whether the 2 models could be some way reunified. There should be some model structure.
Conceptually it's very different because they want to have a non-linear, unstable, elastic path. So and this one it's just, let's say, it's plasticity. So it's linear elasticity plus evolution. So conceptually it's very different. So I don't know again. So I think I should think about it. But sure, we'll be very happy to do that. Absolutely.
No other questions?